Hello, okay, please be seated. So we are soon going to start. All right, so let's get started. So I'm very happy to chair this first tutorial session. So welcome to ICML 18, sorry. And we have the pleasure to have like a first great tutorial by Yisong and Hoang on imitation learning. So one instruction is if you want to ask questions when the speakers ask you to ask questions, please use the microphones, otherwise nobody will understand and hear you. Thanks a lot, and please welcome Yisong.
All right, thank you everyone. It is really a great pleasure to see so many people interested in imitation learning. My name is Yisong. I'm a professor at Caltech, and I'll be co-teaching this tutorial with my student Hoang, who is a PhD student at Caltech. And by the way, the slides are available online, so if you go to the ICML tutorials website and go to the URL for our tutorial website, you can download the slides and follow along if you'd like. Okay. So, imitation learning in a nutshell. So, the basic idea is you're given a training set of demonstrations or Oracle access to a demonstrator. And from that training data, our goal is to train a policy to mimic the demonstrations that we're given as training data. So, in the example here, we see an example of learning to imitate a human in this race car game. So the human demonstrator is playing this race car game, and it gets decomposed into a set of state action pairs, where a state is essentially the screenshot of the game. The action in this case is the steering angle of the controller of the game, and that gets compiled to a training set, and we train a policy to mimic the demonstrations that we've collected. So that's imitation learning in a nutshell. So here are the key ingredients of imitation learning. It varies a little bit, obviously, from application to application, but these are sort of the core ingredients. You start with having the demonstrations or a demonstrator. You often have a simulation environment, or the environment, excuse me, often a simulator. Could be the real world, could be something else. You define a policy class to use for training. These days, it's often a deep neural net, although it doesn't have to be. You define a loss function, an imitation loss function that characterizes the mismatch between a trajectory that your policy executed in this environment versus an expert demonstration. And finally, you use a learning algorithm to optimize for a policy within your policy class within this loss function and this training set. So that's imitation learning in a nutshell. You can think of it as a variant of supervised learning, where instead of predicting a single example IID at a time, we're learning to predict a sequence. So in this tutorial, it's going to be divided into two parts. In the first part, we'll go over some core algorithms and basic settings of imitation learning. It'll be a little bit more technical in terms of the content. And then in the second part, we'll look at various extensions and applications. But first, let me start off with a few teaser results so you can see how imitation learning has been applied already. So arguably, the first application of imitation learning happened in the late 80s through the 90s by Dean Pomerleau and his colleagues at Carnegie Mellon University in training an autonomous vehicle. So this is one of the first applications. And the basic idea is an autonomous vehicle has been instrumented with sensors. A human is driving this. Imitation learning takes over and drives this and steers this vehicle autonomously. Another early application of imitation learning is in helicopter robotics. This was done by Peter Beals and Andrew Wang and their collaborators around 10 years ago. And the basic idea here is an expert helicopter drone pilot is controlling this helicopter drone to do various acrobatic maneuvers. And this data is then collected, and a policy is trained to automatically control this helicopter drone to replicate these acrobatic maneuvers. In this example, the robot is navigating a public space and is inferring the intent of the humans in this public space through imitation learning, and thus avoiding colliding with the human's predicted trajectory. So on your right, you see more of a top-down view where the cyan box is the robot, and it's inferring the intention of the human and avoiding collision. Next, we have an application that I worked on with collaborators at the Walt Disney Company in animation, where we're learning to lip sync a cartoon character in response to audio.
Do I look funny to you? I may be a chimp, but I'm dressed better than you.
I'm a PhD specializing in computer graphics and facial animation. But at night, I'm a level 10 operative for a secret organization.
But we are now on different frequencies.
My speech is pretty good, don't you think? Meu português é ainda melhor, não acha?
Okay, so in this next application, it's an application in sports analytics called ghosting. So what ghosting is you take a replay where the defense did not play well, and you overlay on top of this replay what the defenders should have done. And here, the ghosting players are in white, overlaid on top of a replay, and it's being driven by a deep imitation learning algorithm that was trained on professional soccer players. And the last teaser example that I'll give is in one-shot visual imitation learning. This was done by Rocky Duan and their colleagues at Berkeley, where they are basically learning, using imitation learning to train a policy in a family of tasks. And the goal is to train the policy to be able to adapt to any task within this family using only one demonstration. Okay, now to the boring stuff. Let's start with some notations. So typically in imitation learning and also in reinforcement learning, which is a closely related topic, we have states and actions. States are the inputs, actions are the outputs or the predictions. Our goal is to train a policy, often parameterized, in this case with theta, a parameter vector, that maps states to actions. If this policy is stochastic, it maps states to distributions over actions. And there's often also a state dynamics. This is our model, and this is basically what the simulator or the environment is, which is basically what is the next state given an action applied to the current state. There's a concept known as a rollout, which is basically sequentially executing the policy from some initial state to collect the trajectory of state action pairs. We could talk about distributions over trajectories, which depend on the randomness of the policy and the randomness of the state dynamics. And we could talk about state distributions as well. Okay, so given that notation, here's how we can think about characterizing some imitation learning settings. So here is, again, the race cars setting, which is going to be one of the running examples in the first half of the tutorial. And so a state here is the game screen. An action is the turning angle of the controller. We get a training set from the human demonstrator, pi star, of a trajectory of state action pairs. And our goal is to learn a policy that maps states to actions in a way that minimizes an imitation loss versus pi star. In another example, in basketball trajectories, here, let me just explain what the right-hand figure is. The red lines are the defenders, the green lines are the players on offense, the orange line is the ball, and our goal here is to learn to imitate the behavior of the player in the bolded green line, right? So the state is the location of all the players in the ball, for simplicity. The action is the next location of the target player in question, which is the player in the bolded green line. We get demonstrations of such tracking data. In this case, it's collected from the National Basketball Association. And the goal is to learn a policy that mimics the behavior of this agent. So what are some other data sources one can think of when applying imitation learning? We've already talked about sports and tracking data, games, visual demonstrations. Other things include things like trajectory data from vehicles. This is closely related to human intent modeling application that I described a few slides ago. We can do imitation learning from one black box policy that was trained in some way and try to train another policy to mimic the behavior of a black box policy. There are many reasons why you might want to do this, one of them being model compression in a sequential decision-making setting. And beyond behavior data, we can also apply imitation learning to other sorts of sequential decision problems, most notably optimization problems. So for example, in your top right corner, you see two optimization problems, one continuous, one discrete, and most optimization solvers are in fact sequential decision-making algorithms, and you can actually train a policy to imitate the behavior of such sequential decision-making problems and algorithms, and we'll see some examples in the second half of the tutorial. Okay, so for the remainder of the first half, we're going to start by looking at the most basic setting of imitation learning known as behavioral cloning. I'll draw a contrast with supervised learning, and then we'll look at, take a more detailed look at the landscape of core imitation learning algorithms. So, behavioral cloning. Behavioral cloning is essentially a very simple and straightforward reduction to supervised learning. So here's how it works. Let P star denote the distribution of states that the expert visits when interacting with this environment. So in the racing car example, it would be the distribution of basically game screens that are collected when the expert plays this game, right? What behavioral cloning does is it specifies the following learning objective. Given this pre-collected set of demonstrations by the expert, I'm going to chop it up into state action pairs, treat it each as an IID example, and then apply supervised learning. So given that we're in the current state, my policy should predict an action that minimizes an imitation loss with the correct action. So here the loss function, for example, could be squared error because we're doing regression. So there's a few interpretations of what's going on here. The first interpretation, and there are more than two, of course, so I'm just going to talk about two, is that assuming perfect imitation so far, so we're only looking at a distribution of inputs where we're following an expert perfectly, learn to continue following the expert perfectly. That's one interpretation of what this learning problem is trying to learn. A second interpretation is we're trying to minimize the one-step deviation error along the distribution of states experienced by the expert's trajectory. That's a very literal interpretation of what this learning problem is doing. So let's think about behavioral cloning, which is learning over a very simplified simplification of general imitation learning versus the more general imitation learning problem. So I sort of re-displayed the behavioral cloning learning objective. And the key thing I want you to take away from the comparison is that the distribution of training data is provided exogenously. We query an expert. The expert provides us with a bunch of demonstrations. We treat this demonstration as IID state action pairs, and we train using standard supervised learning. That's behavioral cloning. One variant of a more general imitation learning formulation is shown below, where the key difference now is that the distribution now depends on the policy that we're training. So in particular, if you look at the expectation and compare the expectation of these two objectives, in the first one, the distribution is given to us exogenously. In the second one, the state distribution, it depends on the decision-making of our policy that we're training. Right? It depends on the theta. And so basically what this means is that in behavioral cloning, if we make a mistake, the next state that we get is assumed to be sampled IID from P star. So that's the contrast I'm drawing in the right column in the two images. Whereas in reality what's happening is we start with some distribution over initial states. We give that initial state to our policy makes a decision, and the next state that's inputted to our policy depends not only on the dynamics and the randomness of the environment, but also on the decision-making of our policy, and that breaks the IID assumption. So when might this contrast be problematic if we're using behavioral cloning? And let me just give you one example that highlights a key limitation of behavior cloning, which can matter a lot and sometimes doesn't matter that much. So imagine that we're in this state, and our policy that we train makes a mistake, right? And so we end up being in this state, in the middle, right? Now, we're really close to the edge of the road, and the expert has never done this before. So we don't have a single piece of training data from the expert demonstrations that's pre-collected that has us in this state. All right. What behavioral cloning assumes is, well, you know, my training error is 1% or something really small, and I assume that the states are sampled IID from P star, so, you know, the next state will be sampled IID from P star. However, the new state here is not sampled from P star, right? This is the reality. And so, in the worst case, this type of, depending on your application, this type of behavior can be catastrophic. We could quickly visit new states that we've never trained on, and therefore our behavior is undefined, right? And so here's an example. So on the left is a sample of an expert trajectory for this game. So this was the thesis work of Stefan Ross. And on the right, you have behavioral cloning. And eventually, it enters some state that it hasn't seen before, and then it crashes. Okay, so I've spent the last few slides bashing behavioral cloning, but of course, it is often something that one should try, and one can use effectively in many applications. So, you know, the key advantage of behavioral cloning, and this is one that cannot be emphasized enough, is that it is extremely simple, and there is massive strength in simplicity, right? It's also efficient. It's basically it reduces to one round of supervised learning, which is actually very efficient compared to the other imitation learning approaches. The disadvantage is that there's going to be a distribution mismatch between training and testing, and that may or may not matter. If it matters, it can be pretty bad. And in particular, one application where this matters a lot is when your decision-making setting requires some notion of long-term planning. So you should use behavioral cloning when one-step deviations are not too costly. If you're learning reactive behaviors where you can quickly recover and get back onto the distribution of the expert, and when the expert trajectories, in some sense, cover the state space pretty well, right? You should not use behavioral cloning when the one-step deviations can potentially lead to catastrophic error, and when you're trying to optimize some kind of long-term objective, at least not without a stronger model class. Okay, so now we're gonna continue on with a deep dive into some of the other core algorithms and techniques for imitation learning. So we have behavioral cloning, which I already covered. I'll continue with interactive direct policy learning. In interactive direct policy learning, it assumes access to an interactive demonstrator that you can query, right? And so what that means is, first we collect some demonstrations from the demonstrator, we apply supervised learning to learn a policy, we roll out that policy in our environment, and then the demonstrator then provides feedback on the rollout trajectories of our learned policy to create more training data that then gets fed back into supervised learning again. The cycle continues until we've converged. And so just one loop of this reduces the behavioral cloning, and interactive direct policy learning sort of does this until you converge. And then Hoang will finish the first half by talking about inverse reinforcement learning, where the idea is to train a reward function, and then apply reinforcement learning as a subroutine to learn a policy to maximize this reward function. And the idea here is that this will work well under the assumption that learning the reward function from demonstrations is in some sense more statistically efficient than directly learning the policy from demonstrations. And this will be touched on in further detail towards the latter half of the first half of the tutorial. And here's just another comparison of the core techniques for imitation learning. The top row is behavioral cloning, then we have interactive direct policy learning, then we have inverse reinforcement learning. So in behavioral cloning and interactive direct policy learning, we're directly learning the policy from demonstrations. And you can think of behavioral cloning as a special case of interactive direct policy learning. Whereas in inverse reinforcement learning, we're learning the reward function from demonstrations and then indirectly learning the policy by maximizing the reward in a reinforcement learning subroutine. Behavioral cloning is quite simple in that it doesn't require access to the environment. We simply take the pre-collected demonstration data and we apply supervised learning. That's it. The other two require access to the environment to roll out a policy and then collect feedback. Only interactive direct policy learning requires an interactive demonstrator to be available during training. The other two, behavioral cloning and inverse reinforcement learning, can operate purely on pre-collected demonstrations. So there are a number of other considerations, such as choice of loss functions, when the teacher is suboptimal or partial due to size of the state space and action space, domain transfer, structured domains. We'll touch on a number of these issues in the second half of the tutorial. Okay, so now let's talk about interactive direct policy learning, which is a generalization of behavioral cloning. You can think of behavioral cloning as the simplest example, right? So in order to go beyond behavioral cloning within this paradigm, we require access to an interactive demonstrator that is available at training time to query. Right? And we analyze interactive direct policy learning typically through the lens of what's known as a learning reduction. What a learning reduction does is it reduces a harder learning problem to an easier learning problem, in this case, supervised learning. And there's a general overview of learning reductions available by John Langford. You can follow that link if you're interested. Right. So here's sort of how we can think about learning reductions as it relates to behavioral cloning, right? So here's on your left, which I denoted as capital A, we have the more general imitation learning problem. On the right, noted capital B, is the behavioral cloning learning problem. So we've reduced A to B. And the idea of learning reductions is, well, okay, somehow we've developed more methods for B, right? B is a standard IID supervised learning problem. People have looked at generalization error, sample complexity and stuff like that. So if we know that we can learn well on B, does that imply anything about learning well on A? That's what a learning reduction is interested in. So for example, if we have a PAC guarantee on B, does that imply anything about something like a PAC guarantee on A? And so here are some basic results for behavioral cloning. I won't go over the proofs, and the actual results are more sophisticated. You could refer to the two references in the bottom of the slide. So suppose we have a imitation loss function where if we match the expert demonstration for a specific state, then the loss is 0. That doesn't always have to be the case, but let's assume that's true here. And now suppose in the behavioral cloning problem, we've trained a policy that achieves error epsilon on the behavioral cloning learning objective, which is on the states induced by the expert, our prediction error is epsilon. What we can show is that in the more general behavior imitation learning setting, the error is at most capital T times epsilon, where capital T is the time horizon of the decision making. So how many time steps we're rolling out the policy. And the error then on a T-step trajectory is then T squared epsilon, right? So we do have some guarantees for behavioral cloning for their general imitation learning setting. They're not great. Okay, now let's talk about direct policy learning. So the basic idea is that we're going to construct a sequence of distributions or a sequence of supervised learning problems, right? And that ideally converges to training the best policy in our policy class for the general imitation learning problem. And we typically start with behavioral cloning, which is the bottom bullet point. Now let's talk about how we can use an interactive expert. What an interactive expert is basically a human or a computation or an expensive computational oracle that's available at training time to provide feedback on the state distributions induced by the policy that we're training rather than only by the expert. Right? What that means is that we can query the expert for any state, essentially. And then we can also have a mechanism for constructing a loss function characterizing the mismatch between what our policy is doing versus what the expert would have done on this state, for any state. So on the example on the right, as we're steering the car in the racing car game towards the edge of the road, the expert is providing interactive feedback saying, okay, you should steer it more towards the center of the road. That's the red arrow. And in all the algorithms I'll be describing, they're always applied to the rollout trajectories of the policies that we're training. So we train a policy pi, in an intermediate policy pi in one round of training. We roll out that policy in our environment. We get a sequence of states, and then we ask the expert to tell us what the optimal action would have been to correct for mistakes in any of these states. And in this driving example, if the steering angle is a real valued number, then a loss function could be squared error. Okay, so here's one idea, and this won't work, but it's sort of the first thing you might think of, right? So we first fix a distribution of states, and then we estimate pi. So this is just behavior cloning if we first just collect demonstrations from the expert, right? And then we fix this pi that we've trained, we execute it in the environment, collect a bunch of states, and use that to be the new state distribution, and ask the expert to provide corrections on this state distribution, right? So we can empirically estimate this new p by rolling out pi, and then we repeat. This does not work because it is not guaranteed to converge. We can oscillate, right, between a p and a pi, because we've forgotten the earlier mistakes that we've made in this process. So in some sense, we need to remember all the mistakes that we've made in every step of learning. And that leads us to sequential learning reductions. And so this comprises a family of algorithms that have been proposed to solve the setting with different types of guarantees and trade-offs. So we start with an initial predictor, typically the initial expert demonstrations that were provided to us. And we construct a sequence of learning reductions, and this sequence will be indexed by little m. And so we collect trajectories by rolling out pi sub m minus 1, the previous policy, on the environment, and we estimate the state distribution p sub m using these trajectories. And we often roll out multiple times to collect a large data set. For every state in the trajectories in this rollout, we collect interactive feedback from the expert, what the expert would have done had the expert entered this particular state. And then the details differ a little bit depending on the specific algorithm. So on one side, we can do what's called a data aggregation. And what data aggregation does is it trains a single policy, pi sub m, on the union of all the data sets that and distributions that we've collected so far. It can get a little more, excuse me, it can get a little bit more complicated than this, but that's sort of the simplest setting. And what this means is that pi sub m is training on all the mistakes that have been made so far during every round of training. Another idea is called policy aggregation. And what policy aggregation does is it trains an intermediate policy, pi prime sub m, on only the current distribution of states and mistakes. And after it trains pi prime sub m, it blends pi prime sub m with all the previous pi primes, which is the last bullet point on this slide. And this blending is geometric. And we obtain our new pi sub m by blending all the pi primes. So that's called policy aggregation. Okay, so data aggregation, the core algorithm for data aggregation is called Dagger, which is short for data aggregation. The idea, when you think about how to analyze Dagger, is you reduce it to a sequence of convex losses. So imagine that each imitation loss is convex, and we have a sequence indexed by a little m. Dagger basically reduces imitation learning to a sequence of online supervised learning problems, and the goal is to find a pi sub m that is competitive with the best policy in our policy class in hindsight. This is known as online regret, for those of you who are not familiar with online learning. And there's a number of online learning algorithms that one can invoke that are called no regret. One of them is called follow the leader, which basically is the data aggregation algorithm I presented in the previous slide, where you basically find the minimum pi that minimizes all the loss functions you've seen so far, which is basically the union of all the distributions we've seen so far. And this has regret that is sublinear in capital M, which is the number of rounds of training, which means that we quickly converge to pi sub opt. And The implication then is that there exists a policy that we've trained, pi sub little m, that is competitive with pi sub opt. This is the implication of regret, because if the regret is bounded, that means then the average is bounded, and therefore the minimum is bounded. And so if you didn't follow every detail here, don't worry about it. It's basically reducing to online learning, and there are and then invoking any number of online learning algorithms that have good convergence guarantees to basically converge to a good distribution to train a policy that's close to pi sub opt. Okay, policy aggregation basically trains an intermediate policy pi prime sub m on the current distribution of states, p sub m, and then blends it geometrically with all the previous pi primes. So that basically means that pi sub m is this geometric blending of all the previous pi primes. Right? And recall that pi naught is the expert, which is not available at test time. So the way that you think about analyzing policy aggregation is analyzing that at each iteration of learning, pi sub m is not that much worse than pi sub m minus 1. And in particular, it's at most the quantity in the purple. And by induction, that means that pi sub capital M, the last policy we train, is not that much worse than pi sub naught, which is the expert, right? So now we've trained a policy that's not that much worse than the expert, and there are ways to cancel out the expert in pi sub capital M because it's negligible, because its influence on pi sub capital M decays exponentially. Okay, so just to summarize, and then I'll hand it over to Hoang. What I presented to you is direct policy learning via an interactive expert, which reduces to a sequence of supervised learning problems constructed from rollouts of previously trained policies. And this requires interactive feedback in order to correct for the mistakes made by the policies during intermediate rounds of training. I showed you two approaches, data aggregation and policy aggregation, and they have different ways of learning to correct for all the mistakes that have been made in the past to ensure convergence to a policy that's close to optimal. The specific algorithms that are derived are motivated by different theoretical foundations. The data aggregation by reductions to online learning, policy aggregation by one-step deviation types of analyses, which are also common in reinforcement learning. Right. What is not covered is, well, where does the expert feedback come from? What is the loss function? And this will be fairly application dependent, and we'll touch on some of these details more in the second half of the tutorial. So just to summarize, we've looked at behavioral cloning, we looked at interactive direct policy learning, which is a generalization of behavioral cloning, and now Hoang will talk about inverse reinforcement learning.
Hi, everyone. My name is Hoang from Caltech, and I will be talking about inverse reinforcement learning. But before we go there, though, a very quick intro to the standard reinforcement learning problem. Now, we often utilize the Markov decision process framework, and an MDP is defined by state space S, action space A, a model P that essentially shows the transition dynamics of the environment, a reward function R, which is typically given, and we may also see a discount factor gamma in between 0 and 1 and a starting state distributions. So this is pretty standard for reinforcement learning. And the goal in reinforcement learning is to find a policy that maximizes the long-term discounted sum of rewards, V, which is referred to as the value function. And sometimes we also use the action value function Q, which say that if I start in state S and take action A and then follow policy pi afterwards, then what's my expected long-term reward? Now, the key thing here is that when we know all the components of the MDP, we can use dynamic programming techniques such as value iterations or policy iterations to solve for the optimal value functions. And then the optimal policy will fall out from there. Often, though, we don't really know the dynamics model P, but we can interact with the environment. And one popular way to learn policy is to use model-free reinforcement learning. And there are many, many methods that exist. I'll just mention one here, where we parameterize our policy by a set of weights, theta, such as a neural net. And then we try to optimize for the value function by taking the gradient with respect to theta. The gradient of V with respect to theta is given by the policy gradient theorem. And this is really nice because it's transformed the gradient of V into something that depends on the gradient of the policy and does not depend on the gradient of the unknown dynamics. And this is essentially the idea behind the reinforced algorithm. Each time we execute the current policy to get a trajectory, and then we get the estimate for Q function by summing up the rewards that we see along the way until the end of the trajectory. And so this estimate will let us update the policy parameters theta. This is just a very basic scheme to do reinforcement learning. There are much better methods out there, and if you're interested, you should check out previous tutorials at ICML and NIPS from previous years. Okay, so now back to our purpose. First thing to note is that reinforcement learning typically assumes that the reward function is given. And that is fine for setting like video games, for example, where the reward is simply given as part of the game, but in certain settings it's much less clear what the right reward function should be. So a thought experiment that you can do is imagine trying to write out a reward function for good cooking behavior. Then it's not very clear what range of behavior should be encouraged. And there are, in fact, many examples of unintended consequences of manually trying to write down the reward functions. I show here a recent example from OpenAI. So this video shows a boat racing task. And to encourage the agent to finish the right track, the agent is rewarded for reaching the green targets along the course. But instead of finishing the course, the agent actually learned to cheat the system and get higher reward by going around the circle and try to hit as many targets as possible instead of moving forward. So this is one small example of what could happen when you try to incentivize the agent to do things that you want. Okay, so we see that in many examples, we don't know what the right reward function should be, and the focus of inverse reinforcement learning is to try to learn the quote-unquote optimal reward function, right? And the data that we learn from is a set of demonstrations similar to the previous imitation learning setting that Yisong described, where each trajectory tau here is just a sequence of state and action pairs. And the goal then is to learn an optimal reward function R star so that we can recover the expert policy pi star. And basically, in summary, try to find a reward function that can explain the observed behavior from the expert. So we'll dive into the technical detail of a few algorithms, but here a general recipe for inverse reinforcement learning. We start with some demonstration from the expert. The expert generally is assumed to be optimal or near optimal. And then we parameterize our unknown reward function R by theta. And we start out with a simple case where the reward is a linear functions of known features. And then often, we would update the reward parameters in a loop. And given a reward function estimate, we then try to learn a policy condition on that reward functions. And then we would compare the policy that we learned with the expert data. And so if it's not satisfactory, then we would repeat to find a better set of parameters, thetas, and so on. Okay, so that's the overall structure. But as with many inverse problems, inverse reinforcement learning is fundamentally ill-posed. So let's take this example of the agent here in the white dot trying to navigate the maze from the bottom left corner to the yellow goal block. Now, given just this demonstration, we can't really tell what the reward function may be if the agent happened to bump into one of the red blocks, say. So in this case, you can see that a small punishment or a very large punishment would actually correspond to the same exact behavior. And so more generally, uncovering the optimal reward function is ambiguous. So one thing that we can do to is to relax the original IRL formulation. So in a paper by Peter Abio and Andrew Ng in 2004, instead of trying to uncover the optimal R star and pi star, they actually relaxed the goal somewhat to say that as long as I can find a reward function so that the performance of the optimal policy with respect to that reward is not much worse than the performance of the true expert performance, then I'm happy. And note that this is a little bit different from the original inverse reinforcement learning in the sense that we're not insisting on looking for the true reward function here. Another relaxation suggested by Syed and Shapiro in 2007 is a game theoretic formulation to the inverse reinforcement learning problem. And the goal here is to find a policy that performs better than the expert over a restricted class of reward function. The imitation learning problem here is formulated as a two-player game. On one hand, the reward player tries to find the best possible reward in the class. And at the same time, the policy player tries to push the performance difference between the policy and the expert as far apart as possible. So in both cases, though, we are operating under some friendly assumption. And we are restricting ourselves, first of all, to fully knowing the dynamics model P up front. And when the model is supposed to be given, I will just generically refer to it as model given. The reason is I want to avoid the term model based because that means something else in reinforcement learning. We also assume access to some oracle that, given any reward function, can solve the MDP efficiently. And usually that means that we have small enough of a state space so that this can be done efficiently. And importantly, the reward function we're interested in for now is linear in the known features of state and actions. The class of reward functions that is covered in Syed and Shapiro in 2007 is those with L1 norm exactly equal to 1. And the class of reward function considered under Abio and Ng is the with L2 norm less than or equal to 1. Okay, so now let's see how this linear reward function assumption would help us. We can rewrite the value function of any policy pi in terms of this new reward definition. And now you can essentially pull out the theta outside of the expectation and leaving a term that only depends on the feature of the state that the policy visit, phi st. And we would group this term together and we call these remaining terms mu pi, the feature expectations of the policy pi. So intuitively, mu pi, another way I could put it, is that it is the average of visited state features given a policy. And it's easy to see that if the reward is linear, then finding a policy that matches the expert features imply that the policy is optimal. And this is true regardless of any theta. Expressing value function this way in terms of the feature expectation turned out to be very convenient because we're reducing the inverse reinforcement learning problem into a problem of feature matching, essentially. Now, of course, this is somewhat idealized, right? Because in practice, we can't really estimate this quantity, mu pi star, exactly, because we only have limited number of demonstrations. So in a way, this problem is also ill-posed, similar to the original inverse reinforcement learning problem. And so we need to apply some restriction. Now, one such restriction from Abio and Ng is that we relax the problem to become finding a policy pi so that the feature expectations of pi and pi star differ by no more than some epsilon. And to see why this is good enough, here's a short proof using essentially Cauchy-Schwarz inequality. And because we're limiting the set of reward parameters to one with L2 norm less than 1, so as long as we find a policy who expected feature close to the experts, then the performance of that policy will be guaranteed to be close to the expert policy as well. And so here's the algorithm sketch. For each iterations, we solve a max margin problem. These optimizations basically try to find the max margin of the expert feature from all the policy that we have found so far up to this round. And every time we solve this optimization, we got a new reward estimate. So if we refer back to the diagram that we have before, this is only the update reward step. Of course, we have those assumptions, so let's use them. Using the MDP solver Oracle, we can get an optimal policy with this, with respect to this reward estimate. And because we know the dynamics model, we can compute the features of the expectation of this new policy, and then we can compare that with the expert and so forth. And the algorithm would stop when the margin found is less than some desired precision epsilon. And in the paper, the authors proved that the algorithms need at most this many iterations, where k is a dimension of the state feature and gamma is a discount factor of the MDP. Okay, so this max margin approach was also used in the paper Maximum Margin Planning by Ratliff et al. In 2006, where the authors actually attempt to generalize this setting to multiple MDPs. And I also previously touched on the game theoretic formulation from Syed and Shapiro, and the overall scheme is actually similar, except that the reward parameters are updated using multiplicative update weight update algorithms, instead of solving a quadratic program as we saw earlier. And the common theme of these work is that they share the same features of relaxing the inverse reinforcement learning problem to one of feature expectation matching. And just a quick recap, the idea is that we find a reward so that the optimal policy with respect to this reward matches the expert feature. And since looking for this reward is ill-posed, so we are restricting our reward search to resolve this ambiguity. And this effectively can be viewed as a form of regularization. And now I'd like to discuss another regularization scheme, which is maximum entropy. So to motivate the maximum entropy method, let's recall that we talk about how, given the same expert demonstration, many reward functions could correspond to the same policy. So we sidestep this problem in a way, and we say, okay, feature matching will give us a near optimal policy anyway. But think about the eventual goal, right? If we want to find a policy that could explain the expert behavior, then we could basically create any two policies that match the expert feature, and we can create any stochastic combinations of them. And the resulting policy will also satisfy the feature matching requirement. So in a way, we still have the ambiguity of deciding which one is the right policy. And maximum entropy principle gives us actually a principal way to resolve this issue. First, we notice that executing any policy pi over the state space will induce distributions over possible trajectories. Let's call that p tau. And we'll reason over the distribution of these trajectories. First, we can rewrite the feature expectation matching requirement that we saw before as simply summing over all possible trajectories induced by pi. Two things is that one, the sum should match the expert feature, right? And second, it should sum up to 1 to be a proper distribution. So now, given this constraint, among possible distributions of trajectory that satisfy these, which one should we choose? And the maximum entropy principle, as discussed by Jaynes in 1957, state that we should choose one that with the largest entropy. And to state it another way, we should pick one that explains the data without overcommitting. So we could essentially express this principle as a constraint optimization problem, where the first constraint here in practice is just an empirical average of the expert feature coming from the demonstrations, right? Because we don't have access to true expert feature mu star. Okay, so from here we could turn this constraint optimization problem into an unconstrained one by forming the Lagrangian. It's pretty standard technique in optimization, and trying to maximize this Lagrangian. We're going to set the gradient with respect to tau to 0, and after some derivation, we will see that the distribution that maximizes the entropy, given the linear feature matching constraint, is actually in the exponential family. And in particular, if the reward is linear in the known feature, as we discussed before, then the max entropy distribution of trajectories, given the reward parameters theta, will depend exponentially on the inner product of theta and the feature of trajectory tau. So going back to the inverse reinforcement learning setting, what does this mean for us? It means that the probability of a trajectory with high reward is exponentially more likely to be sampled from an expert than trajectory with low reward. And basically, this is the formulation behind the paper Maximum Entropy Inverse Reinforcement Learning by Zebart in 2008. So given a reward parameters theta, the conditional probability of trajectory will take this exponential form divided by the partition function, which is sum over all possible trajectory, which actually seems kind of tough. But as we'll see for now, in a model given context and a small MDP, we don't really have to worry about so much about this partition function for now. But our goal is how do we learn the reward function given this formulations? And we're gonna learn the reward function by maximizing the log likelihood of the observed data under the distributions derived here. So taking the log likelihood breaks the product into the sum of conditional probability of each expert trajectories given the parameters theta. And we're going to use gradient descent over this objective to maximize the likelihood. In particular, in this case, since we know the model and the reward is linear, the gradient can actually be expressed in this closed form. The first component is just the empirical estimate of the feature expectation of the expert, which we can calculate easily. The second component is actually trickier. It's a sum over all states and depends on the state visitation frequency D sub S under the current policy. And the author suggests that we can use dynamic programming to efficiently calculate this visitation frequency measure. And concretely, at times t plus 1, the state visitation frequency depends on those from times t, and also depends on the current policy pi, and the transition dynamics from S to S prime, which is supposed to be known because we are given the model. And again, here pi theta comes from an MDP solver that gives us the optimal policy with respect to the current theta. So basically, this is how we are updating the reward parameters in max entropy inverse reinforcement learning. And so far, we focus, here's a good place to summarize the inverse reinforcement learning technique so far. So far, we focus on pretty simple setting. We assume that the reward is linear in some known feature. And for each iteration, we actually need to solve a full reinforcement learning problem. And this requires essentially to know the dynamics of the MDP upfront, which is not always realistic. And it really only works for low dimensional setting because solving RL in the inner loop can be very expensive. So now let's discuss generalized setting where we don't know both the reward and the dynamics. Can we consider complex reward function that can be represented by a neural network? We will assume that we have access not to the full dynamics, but access to interacting with the environment or a simulator, and we'll try to scale up to a large state space. And this is where we're going to go next. Okay, so one generalization is the guided cost learning algorithm by Finn et al. In ICML 16. Here, the reward function is parameterized by a neural network. And we're going to start from the same maximum entropy formulation as before. And except for now that, as you will see, the partition function is going to be an issue. But in any case, we will still try to learn theta via maximum likelihood. But except now that we can simply break up the gradient in terms of the state features anymore because the cost is no longer linear. Instead, now we have to address the partition functions z here which again will sum over all possible trajectories. And calculating z in general is not tractable in high-dimensional setting, so we need to sample to evaluate the likelihood and its gradient. And after we can estimate the gradient of the likelihood, then we're going to be able to update the parameters theta. So that's going to be our goal. Okay, but the key idea in approximating z is to sample from a proposal distributions Q over some trajectory. And then we're going to form unbiased estimate of z by averaging over this sampling distribution with the exponential reward weighted by the proposal probability. And this estimate of z, as we discussed, will allow us to estimate the gradient of the likelihood for optimizing the reward function, right? But the question still remains, which proposal distribution should we choose? So turns out we can derive this. The optimal of such proposal distribution actually is the distributions induced by the optimal policy, which we don't know, right? So this requires doing policy optimization. But ideally, we would like to avoid doing a full reinforcement learning routine. And just for your reference later, I include the derivation of the estimate of the gradient here. You can go back and to see it if you're interested. And so this is a high-level overview of the guided course learning algorithm. For each loop, say we have a current policy, we would generate sampling distributions, which are a set of trajectories not far away from the ones induced by the current policy. And these sampling trajectories are then combined with existing expert demonstrations, and we can use them to estimate the gradient of log likelihood to update the reward parameters. And then using this estimated reward, instead of solving the full reinforcement learning problem, we're just going to do one gradient step of model-free policy optimization. And this improved policy will in turn presumably generate better sampling distributions for subsequent iteration. So there's an analogous connection here between this update loop and generative adversarial network, where the policy is playing the role of a generator, trying to generate samples similar to the expert demonstrations, and the reward function is playing the role of a discriminator, trying to assign high reward to expert trajectories and low reward to the policy induced by the learning policy. And this connection between imitation learning and generative adversarial network was the focus of a paper, Generative Adversarial Imitation Learning by Hoang and Amon in NIPS 16. So in the next few minutes, I'm going to derive this connection, but from the feature matching perspective. So let's go back to 2008. Syed and others proposed an approach to do direct imitation learning. Back then, they also called it apprenticeship learning via matching occupancy measure. So occupancy measure, d pi, intuitively is the visitation frequency of state action pair S and A if we follow the policy pi. And this is a more formal definition of d pi. By the way, we can think of this as feature expectation of pi, where the feature vector is indicator function instead of phi. And a simple fact about occupancy measure is d pi is that we can express the value function v as a linear combination of reward function over possible state and actions. And notice that this is actually true regardless of whether reward function is linear or not. So then, similar to the idea behind feature expectation matching, the imitation learning problem now can be reduced to one of occupancy matching. Now, we're not saying that we have to find the optimal reward. Rather, we're saying that if we can match the occupancy measure with the expert, then for any reward function, including the optimal one, the value functions will match that of the optimal policy. And so from here, Syed and others propose to solve a linear program, which is the dual of the original MDP. And two things to note here. First is that actually in their algorithm, there is no reward learning. So under this scheme, we don't really need to solve the full reinforcement learning problem iteratively. And the second thing is that we can think of this occupancy matching problem as a dual of the original MDP problem. So generally, though, the occupancy matching problem is not well posed, similar to the matching of the feature expectations that we saw a few slides ago. So we can once again try to employ maximum entropy principle and consider this relaxed version where we can maximize the entropy subject to the occupancy measure, d pi and d star being closed under some sort of distant metric. And this gives us a constraint optimization problem. And again, forming the Lagrangian and turning this into an unconstrained optimization problem, we arrive at this highlighted objective. And note that in general, there are many ways for us to pick the distant metric between d pi and d star. And so now we arrive at the formulations, which is the great starting point for generative adversarial learning, generative adversarial imitation learning, or GAIL, from Ho and Ermon in 16. In particular, the distant function that they consider took this form, which is also referred to as the Jensen-Shannon divergence. And so this is the final optimization objective of GAIL. There's a close connection between imitation learning and generative adversarial network here, where the idea is we can pick a neural network to be a discriminator, which is D here. The discriminator tries to classify a sample from the expert as 0 and a sample coming from the policy as 1. And we can train the discriminator by updating the network weight, by applying this gradient, and basically this discriminator tries to maximally tease apart the expert and the policy trajectories. And the policy, on the other hand, is acting like a generator that tries to generate samples as similar to the expert demonstrations as possible, right? We are assuming here that we have access to the environment or a simulator of the environment, and the generator can improve its ability to output realistic sample, essentially, by taking a policy optimization step as well, similar to the guided cost learning algorithm. So the overall architecture of the two algorithms are actually share high-level similarity, but the way that we derive it here is more direct. And so with this, I want to summarize the different approaches under inverse reinforcement learning. And so far, we have discussed an evolution of different inverse reinforcement learning idea. We started from simpler setting, and we work up to a more complex setting, complex model-free setting. In either case, the schematic of the inverse reinforcement learning solution is generally an iterative three-step process, where in each iterations, we're going to update our reward estimate, whether linear or neural net representation. We go from solving a full reinforcement learning problem in each iteration, which basically limit us to small MDP, to doing single-step reinforcement learning update. And essentially, that allows us to work with continuous state space MDP. This fast reinforcement learning update is possible also thanks to all the advances of stochastic optimizations, particularly with deep neural network. And we go from simpler setting where dynamics is supposed to be known, which allow us to compare policy performance of the expert with the expert easily, to the model-free case where it's trickier, but we replace the requirement of knowing the dynamics with an access to environment or simulator to gather more data. And essentially, we unify these two perspectives using occupancy measures and the maximum entropy principle. So here's a list of the papers that we have covered in the first half of the tutorial. Now, we are happy to answer any questions that you may have.
So if there are questions, we're happy to answer. Otherwise, we start the second half of the tutorial at 10:30 a.m.
Is there a microphone?
Yeah, they have microphones. Yeah.
I have a question. Oh.
Yep.
Hello. Yeah, so I was wondering, Dagger versus CERN. So what were your thoughts in terms of their properties?
Well, since if you look at the analysis of Dagger versus CERN, learning reductions, the analysis is always relative to the strength of the policy class. And so the reductions, in some sense, you can't say anything super conclusive because it could be that the way you do the reduction in CERN leads you to an easier supervised learning problem than you get in Dagger. So assuming that the supervised learning reduction gives you the same efficiency, which you cannot say until you actually run it on the application, then Dagger is more efficient.
Hi. I was wondering if for the imitation, behavior imitation, is the performance, like for example in the racing game, strictly constrained by the performance of the expert?
So in all the applications and settings we looked at, the performance is constrained by the strength of the expert.
Hi, can you hear me? I'm here. So the first thing, which was the behavior matching or behavior, I don't know what you called it.
Cloning.
You said that the problem is that all the states are sampled from the demonstration. Therefore, the actual policy might wander into a region which it hasn't seen in a demonstration. That also seemed to be a problem for the maxent method because it also just, the likelihood you actually sample from the real data and real trajectories. Do you also see that a problem with the maxent method?
I would say that it's a little bit different. So the first part of your questions, the way that I would address that is behavior cloning, you run into a problem, particularly when you run into a setting where you have partial observability, where your contextual features does not really capture the full state information. And so therefore, learning policy directly, as Yisong discussed in the first half of the tutorial, is actually tricky. Now, max entropy method is a little bit different because you're trying to capture the cost information. And so in a way, it runs into a different set of problems where even if I have the full set information, the reward learning problem is still not very well posed. So max entropy actually is a way to help you regularize that, regardless of whether you have full observability or partial observability, if that makes sense. So yes, in a way it is a problem, but it's a different problem, if that makes sense.
Hey, I have a question here. So for the racing game you were using for testing for experiment, so for the inputs for state, do you do any pre-processing for the graphic or you just using the raw pixel?
So that's a fairly application-specific question. Certainly, if you are using modern methods, such as based on convolutional neural networks, the amount of pre-processing of the pixels is necessary is fairly minimal these days. In the earlier work, where they largely relied on linear functions, then there was a lot of pre-processing of the pixels.
Okay. Another question is, how do you collect the input? I mean, you have your keyboard, you have another process or program to connect the user inputs?
Yeah, you're just keylogging all the inputs of the game controller.
Yeah, because I mean, is there any kind of delay? Because when you turn left or turn right, I don't know if the human input has any delay, and is there any kind of effect on the algorithm?
You want to answer that one?
The delay? Yeah. So in certain applications, it is actually an issue. I suppose that for the example of the racing game that was discussed in the first half, that's a lot less of an issue. But in the second half, we're going to discuss one particular application where the learning agent tries to gather human feedback. And because of the speed that the human can give feedback, it's actually a lot slower than what the computer can handle. Then we're going to have to try to accumulate the human feedback in a certain ways. But yes, it could be a problem.
Okay. I'm looking forward to the second part.
Oh, hi. So one of the core difficulties mentioned was that there are multiple reward functions that can explain the expert behavior. So do you think that Bayesian methods could be used here, for example, to learn a posterior over the reward function parameters?
Yes, I think so. But I mean, I guess under Bayesian methods, the way that you use the prior is basically equivalent to some form of regularization as well, where you're encoding your prior information into it. So it's another form of restricting your reward inference, if that makes sense. It's similar to the previous two methods that we discussed, where you're going to try to restrict your reward parameters to have L1 norm equal to 1, for example. Right?
Right.
Yeah.
Hi. About the last part of the presentation where you talked about the similarities between imitation learning and GANs, generative adversarial networks.
Yes.
How tightly are these coupled now based on those results? And does it mean that everything that's happening in GANs to stabilize them and all research is directly applicable to this problem of imitation learning as well?
Well, so the answer to that question is the formulation of GAN, or the paper that introduced Gale that I discussed previously, did have some problems with some extension, or depending on the application. So in particular, in the second half, we're going to talk about one applications where the expert trying to demonstrate the kind of trajectory that have multiple different modes. So as you may know, GAN faces problem of mode collapsing.
Yeah.
So using Gale for that purpose faced a problem, and there was actually a follow-up paper that tried to address that issue.
Thank you.
Hi, this is on the assumption of a linear reward function. So how good is this at approximating, say, like non-linear reward functions? So how does it perform with different types of reward functions of non-linear forms?
So to really answer, so answering these questions fully is actually tricky because, so one thing that I would point out is that the reward function in this setting, in the simpler setting, is assumed to be linear in known feature, right?
Oh yeah, linear in features, yes.
Right, so they never really
fair enough,
talk about what those features could be. Now in principle, you could have some very expressive feature, right? And that could be very good.
Right.
Or you can have very, very bad features and it's not going to get you anywhere.
Right.
So it really depends.
Right, so it's actually much more general than it appears then, since the features can be very
That's right.
expressive.
The only thing that makes it, less general, I guess one of the things that make it less general is that these features are supposed to be known up front.
Oh, okay.
Right? So if you have a neural network, then you have a lot more flexibility in terms of choosing these features.
Okay.
Yeah.
Thank you.
Yeah, it was great. What?
Did you add more slide from the other day, or is it kind of the same?
For what, for my part?
Yeah.
Almost the same. Okay, we'll be starting soon. All right, welcome back to the second half of the tutorial. In the second half, we'll be looking at various extensions and applications of imitation learning to a wide range of settings. We're going to start with one of my personal favorites in speech animation. I gave you a teaser result in the very beginning of the tutorial. I'm going to just spend a couple of minutes telling you a little bit more of the details. And so here is the high-level idea. It's from a paper titled The Deep Learning Approach to Generalized Speech Animation. It was a project I worked on in collaboration with the Walt Disney Company. And so here's the idea. We have an input sequence. Here we'll use X, which you can think of as an input sequence of phonetics. And then we have an output sequence. Here we're going to use Y, which in this case is an output sequence of deformations of a face model. So Y, each token in the sequence Y is d-dimensional, and you see on the right an illustration of how one can collect such data. Here is an actor, he is speaking sentences, and we're watching this actor's mouth move as that person is speaking sentences, and we built a mouth model that is, in this case, has 30 degrees of freedom, so d equals 30. And the goal then is to learn a predictor pi that maps from sequence of X to sequences of Y. And so you see in the bottom part an example. So X here is a frame-by-frame decomposition of a phonetic decomposition, of the word prediction. And here the temporal resolution is 30 hertz. And in the very bottom, we're visualizing the first dimension of a d-dimensional, a 30-dimensional face model. And the first dimension corresponds to how wide open the mouth is. So when the first dimension is large, the mouth is wide open. When the first dimension is small, the mouth is closed. So as we start saying the word prediction, the mouth sharply opens, and then stays open, and then closes a little bit, stays at that level of openness, and then closes some more. So this is the prediction problem. And without going into the details of the learning algorithm, we're basically doing behavioral cloning. So with a few little tweaks that we don't need to go into details, just basically the behavioral cloning method that you saw in the first half. And you get results that look like this. Note that since we're mapping phonetics to animation, we, in some sense, are language independent as long as you plug and play with the correct speech recognition software.
Deutsche Wörter sind sehr viel länger als englische Wörter. Mal sehen, ob das trotzdem funktioniert.
한 가지 언어는 충분하지 못해.
Jeśli kiedykolwiek będziesz odwiedzał Polskę, polecam Kraków.
මම දළදා මාලිගාව වැඳීමට සෙනසුරාදා හවස ගියෙමි.
你们真讨厌，吃饱了喝足了就坐那儿看我说话。So that was me speaking Chinese. We can do singing.
Oh, Danny boy, the pipes are calling. from glen to glen and down the mountainside.
And so just to give you a glimpse of how this project came into being, it was designed and originally motivated to fit into a production pipeline, such as those you would see at animation companies, such as at Walt Disney Animation. So you have your input audio. You use off-the-shelf speech recognition. You get phonetics, and you feed that into the model that we trained, the predictor that we trained. And then you can use standard computer graphics techniques to retarget from our intermediate face representation to any animated character. And then you import that animation to editing tools such as Maya, and then the animation artist can inject low-frequency edits such as smiling on top of the high-frequency animation of the lip syncing, which is at 30 hertz. So that's basically how it works. Next, I'm going to move on to imitation learning for structured prediction and learning to search. So structured prediction, the idea is to learn a mapping from some structured input space X to some structured output space Y, right? And typically, because the output space is structured and often combinatorially large, this requires solving an optimization problem at prediction time. Perhaps the most common example is the Viterbi algorithm for running map inference of hidden Markov models, where the structured output space is the space of all possible sequential outputs. And so there are many, many instances of structured prediction. And in fact, arguably the vast majority of prediction problems that we actually are interested in the real world are structured prediction problems. We just often don't treat them as such. So other examples include tacit NLP. So if X is a sentence, Y can not only be just a sequence, like a part of speech tag sequence, but also can be an entire parse tree. So the output space is the space of all possible parse trees, which is combinatorially large. If X is a body of text and Y is a clustering of all the noun entities, named entities in that text for what's called noun phrase coreference clustering. If X is an amino acid sequence, we want to predict, for example, in Y, the 3D structure of X, right? These are all examples of structured output spaces. Other examples include, this is a classic example in computer vision, which is stereo vision. X is a pair of binocular images, and Y is the depth map. And the structure here arises from the fact that we want to model spatial correlations. So the depth of two neighboring pixels should be similar to each other, all other things being equal. We can predict things like rankings, which are very common in applications in information retrieval and recommender systems. And the space of all possible rankings is also combinatorially large. Robotic trajectory planning, routing. Routing is a structured prediction problem. And things like conservation planning, where you want to do planning for conservation areas in an urban environment, satisfying constraints such as the fact that they're all connected and other sorts of ecological constraints as well. So these are all just a few examples of the many, many, many types of structured prediction problems in the world today. And so let's sort of get into a little bit more of the technical details with the simplest version of structured prediction, which is sequence labeling. And the most common example here is part of speech tagging. It's also quite common in various computational biology applications as well. So in part of speech tagging, which is an NLP application, we're given a sequence of words, X, and we want to predict a sequence of part of speech tags, Y. A part of speech tag are things like noun, verb, adverb, adjective, determiner, etc. And so because the space of all possible sequences is exponentially large, we typically use some sort of optimization procedure. In this case, we're going to use dynamic programming, such as the Viterbi algorithm. And the goal then is to find a parameterization of the cost function before we run dynamic programming, such that we minimize a global loss function over strings. In this case, let's just say it's Hamming loss. Okay, so when we phrase this as an imitation learning problem, the most common way is to learn the decision function, right? So our goal is to use imitation learning to learn the sequential decision function that actually solves this optimization problem at test time, right? So here's an example of how that might work, right? So we have our policy pi that's going to sequentially predict all the output tokens of this part of speech tag problem. So the action is basically predicting an output token. And so let's start with the first state, which is basically in this case represented as the concatenation of the input sentence X and the fact that we haven't predicted anything yet. That gets fed into the policy. The policy predicts a part-of-speech tag. The next state is the concatenation of our input sentence with the fact that we predicted the determiner in the first token. We feed that into our policy. Our policy predicts the next part-of-speech tag. And this process continues. And so the goal then is to learn this pi, right? If we can learn this pi, then we can learn to use it for this particular structure prediction problem. And throughout this part of the tutorial in structure prediction, we're going to look at it from the viewpoint of interactive feedback, or in other words, interactive direct policy learning. Okay, so let's run through how this might work using Dagger, which is one of the interactive direct policy learning algorithms that we talked about in the first half of the tutorial. You could use other ones as well. This is just simply for simplicity. So in iteration 1, we've memorized the training labels. In this case, the ground truth sequence labels. So that's pi naught. So we roll out pi naught. And what that means is we have our first state, which is the input sentence, plus the fact that we haven't predicted anything yet, and pi naught predicts the determiner in the first part of speech tag because it always predicts the correct answer. The second state is x concatenated with the fact that we predicted the determiner in the first part of speech tag, and then pi naught predicts noun because it always predicts the correct answer, and this process continues, right? What Dagger does is then it collects interactive feedback. Here, interactive feedback is collected by querying the collection of supervised labels from the structure prediction problem. So we have all the correct part of speech tags. That's the action. That gets treated as the trajectories to estimate our distribution of state action pairs from the rolling out pi naught. And then we train a policy, pi1, on p1, or in this case, an empirical estimate of p1. In iteration 2, we run our train policy pi1 on our input instances. And here, we make a mistake, right? So in our first state is the same as before, but our policy pi1 predicted noun in the first part of speech tag instead of determiner, which is the correct answer. Now, the second state is a state that we've never seen before, right? In the initial training data, because the initial rollouts are based off always making the correct prediction. So now the second state is the input sentence x and the fact that we predicted noun in the first part of speech tag, and so on and so forth. So we roll out pi1. We again collect the correct labels by querying the structured labels that are given to us for training. And so we're basically learning in the second state to correctly predict noun, even though we incorrectly predicted noun in the first part of speech tag. So we were learning to recover from having made a mistake. And that gets constructed into a second training set, or an empirical estimate of a second training set, P2. And we train pi2 on the union of P1 and P2. This is Dagger. If we were doing CERN, we would train a different policy on each one and stochastically mix them. And this process continues. Now we roll out pi2. Pi2 now predicts the determiner correctly in the first set, in the first state. And then it makes, for whatever reason, it makes a mistake in the second state, and it predicts verb instead of noun. And then now we collect a training set that can learn to recover from making a mistake in state S3. And we train pi3 on the union of pi1, pi2, and pi3, and this process continues until we've converged. So that's basically how you would apply interactive direct policy learning to structure prediction problems. So here are the basic ingredients. The key idea is that we want to deal with distributional shift. The distributional shift in this case is basically whenever the policy makes a mistake, we need to learn to recover from the mistakes while we're doing inference in the structure prediction problem. This is related to other approaches that have been proposed recently, such as scheduled sampling. Another issue, and I'll touch on this more in just a little bit, is that you want to design the imitation loss in the reduction to be compatible with the high level, with the original structure prediction loss. In the example that I just gave you, the structure prediction loss was Hamming loss. Now, Hamming loss is particularly easy to deal with because it's completely additive. it completely decomposes additively per token in the sequence. And so one could just construct 0-1 classification loss on the multi-class labels at each step in the decision-making of the sequence labeling. And you can show that doing that well lifts to doing well on Hamming loss, because Hamming loss is trivially additive. More generally, we need to reduce to cost-sensitive classification. And there are also efficiency considerations, such as running this, all these different modules quickly, and in some cases, doing it in a fully differentiable way to take advantage of recent advances in training deep neural nets. And so now I'm going to give you just a little bit of detail on one example where we actually have to reduce to a cost-sensitive classification error because the original loss function was not trivially additive, right? And this is a paper called Learning Policies for Contextual Submodular Optimization. And the basic idea is as follows. We have a training set of context, comma, submodular functions. So x is the context, and f sub x is a submodular function, monotone submodular function associated with that context. And the goal is to learn a pi that greedily or sequentially maps x to an action set A to maximize f sub x. So for those of you who don't know, submodular functions are set functions that map sets to real values. And typically in the maximization setting, one wants to select a budgeted subset of the ground set of actions that maximizes f sub x. And the greedy algorithm, which sequentially grows the set, is sort of the most widely accepted way of doing so. But now we want to learn a policy that does this without having to actually query f sub x. And so here's the learning reduction, right? So at each state, we have, is described by x comma a, where a is the set of already selected actions. And now we need to create a training example from this state in order to train the policy to mimic the greedy algorithm as well as possible. And how we do so is first we define an f sub max, which is the max possible incremental gain in the submodular function from adding any action to the action set. And then we construct a cost function, which is not 0-1 loss, but depends on what I call the greedy submodular regret, which is the difference between the submodular gain of taking any particular action versus the maximum possible submodular gain. And now we construct a supervised training example of that input state plus this cost vector of overall possible actions, and that is fed into a supervised learning algorithm. And then you could wrap Dagger or CERN around this approach, and you can now show that minimizing this cost-sensitive supervised learning error in the reduction will lead to a near optimal policy in your policy class overall. Okay, so another perspective on structure prediction is that it is similar to, or in many cases, equivalent to some kind of learning to search problem, right? So what is learning to search? Well, learning to search basically says we have some input description, X, and we compile it into a search problem, a combinatorial search problem, typically, right? And we then want to train a policy pi to effectively or efficiently navigate this search space, right? And there's a few different considerations. There's some high-level supervised reward or cost function that we're trying to maximize or minimize, such as routing cost, the blue score if you're doing translation, Hamming loss, submodular utility, Jaccard score, et cetera, et cetera. And we want to train a policy that, in this case, reduces to a set of supervised learning problems where the supervised learning error guarantees lift back up to doing well on the original high-level reward or cost. Another issue that comes up here, which is something that I touched on very briefly in the first half of the tutorial, is that the expert here might be weak, right? So even though this problem is fully supervised, in many structured prediction settings, computing the optimal solution can be combinatorially hard, or computing the optimal recovery from an imperfect intermediate solution can be combinatorially hard. And so in that sense, the expert is weak, right? The expert is some computational oracle in the structured prediction problem. And so here's one completely different example of learning to search, which is learning to search in branch and bound algorithms. So this is used to solve things like integer programs, right? So integer programs are typically solved using a search heuristic known as branch and bound. And you see a depiction of this in the bottom, where basically you choose, at each part of the search process, you choose an integer variable that you want to set, and then you and then you branch on that setting that integer variable, in this case if it's binary, on either 0 or 1, right? And typically in branch and bound, there are two local decisions one make: a pruning and a ranking and a pruning. Ranking basically ranks all the integer variables to the ones that you want to set first, and pruning is eliminating integer variables from consideration, or settings of integer variables consideration that you know cannot be optimal. And then the idea is to train a policy class that actually is a combination of two policy classes, one for ranking, one for pruning, and you could train using solved instances of integer programs, such as those provided to us by an off-the-shelf solver such as Gurubi. And the idea is to train this policy to solve these instances more efficiently, or to generalize to new instances that you don't have solutions for. And that leads me to talking about suboptimal experts, right? So here, the issue of having a suboptimal expert really comes into the foreground, right? If you have a really large integer program, you don't actually have, the optimal solution, the optimal integer solution. You have a suboptimal solution. So how does one get around this? One is, well, if we have query access to the environment, such as what we typically do in reinforcement learning, we know the quality of a solution, right? We just only have suboptimal demonstrations of finding suboptimal solutions. So by having query access to the environment and blending a little bit of very simple exploration, such as epsilon greedy, with various imitation learning algorithms, we can learn to imitate. We could use imitation learning to learn a policy that actually is better than what the teacher can provide us. We could do more sophisticated exploration, which combines things like contextual bandits. And there are other approaches that take a more reinforcement learning-centric interpretation of this problem, such as taking an actor-critic style approach to this structure prediction problem. And so let me just give you just a small description of one such example, which is called, from the paper, Learning to Search Better Than Your Teacher, by Chong et al. In ICML 2015. And here I have to introduce just a simple concept called a roll-in, which is a little bit different from a rollout. In a roll-in, you execute a policy without any considerations for learning. And then in a rollout, which is what we talked about before, we execute some other policy and use the information from that rollout for learning. So here, it's again a sequential decision-making problem in the search space. And we roll in from a policy until some time step, and then we look at all possible one-step deviations of that state that we end up in after roll in, and then we roll out using some other policy to collect reward. And so what this paper analyzed was different combinations of roll in and roll out. And so if the expert that's providing us labels or trajectories in the search space is not optimal, then you actually want the roll-in to be from your learned policy, and your roll-out to be from a mixture between your learned policy and the expert policy. Now, CERN, which is one of the methods we discussed in the first half, is in the bottom left corner, and it is not optimal if the reference or the expert is not optimal. And so this is a generalization of CERN in some sense, that can learn to do better than the expert. Okay, another issue that is you can think of as a special case of structure prediction is time series modeling, such as time series forecasting, right? So I have here a very simple equation of a time series model where the next state, t plus 1, is equal to some dynamics model, f, applied to the previous state, x sub t. If this dynamics model is stochastic, then in this case, we take the expectation. It's the expected next state. And so to do forecasting, the goal then is to learn a policy pi that maps x sub t to x sub t plus 1, right? So in a sense, the input is the input to the policy is the policy's own previous prediction. And so this is a special case of sequence prediction because the input is fully determined by the previous prediction. Okay. So again, we apply interactive imitation learning. So if the red line is the ground truth of the time series model, of the time series data, and the gray line is the prediction of a policy that is making mistakes, then we interactively provide feedback saying at this particular state you should be predicting that something that's actually on the ground truth trajectory in this time series model. So this is an instance of interactive imitation learning where the expert policy is basically arises from the data itself. And one can also extend to latent variable models. This is a fully observed dynamical system. One could also extend this to latent variable dynamical system models as well. Okay, so just to summarize, what I presented to you in this part is applying imitation learning to structure prediction problems. And the key idea is that we want to learn the decision function or the inference function to navigate some search space. This reduces to interactive imitation learning, where we get expert feedback for some computational oracle derived from the supervised structure prediction problem, when the supervised structure prediction labels. In some cases, this requires a careful choice of the loss function because the overall reward or cost function in the structure prediction task, it can be highly non-additive. And so you need to do some careful design of the supervised reduction in order to lift guarantees from the supervised learning problem back into the original problem. And in many cases, because the search space can be combinatorially large, you have experts that are suboptimal, right? Because since the experts are derived from computational oracles at training time, if they're suboptimal, then we need to have ways of actually learning policies that perform better than the reference expert. And so with that, I'm going to turn it over to Hoang to talk about a number of other applications.
Hi everyone again. So for my part, I want to switch gear a bit and discuss a number of topics and papers that don't necessarily fit in neatly into the class of techniques we have discussed so far. And mainly I'm going to try to discuss extension and recent applications of either imitation learning or inverse reinforcement learning. And I will group recent work into a few topics, and given the time, we have way more papers than we would like to have time to cover, so it's hard to do justice to all of them. But I'm going to try to group them into some somewhat coherent manner. So first, we have been talking about imitation accuracy as a key optimization objective. But there are settings where imitation accuracy alone is not sufficient. And here is a concrete example of what I meant. This is an application of our smooth imitation learning work from ICML 2016. On the left, you have a human actually filming an event, in this case a sport event. And the goal is to have an autonomous camera, as you can see on the right, learning from this type of demonstrations to be able to film event autonomously in a human-like manner. So that's the goal. So what's the learning problem here? First, we can extract certain contextual feature from the scene, like noisy detections of objects, such as humans in the scenes, etc. And the state will be composed of recent contexts and actions, where actions here is the angle that the camera is pointing to effectively. And the expert actions is a camera angle of the actual human filming the event. And now the goal is we want to learn, the imitation learning problem is we want to learn a policy that sequentially map the state feature to the right camera angle, right? So now, if we just use behavior cloning to imitate the expert, we see from the plot of the test time actions that the imitation accuracy actually on average is quite good. But this is nowhere near being acceptable or for our purpose because the sequence of actions is extremely noisy. And the issue here is that we actually need both imitation accuracy and actions being smooth. And the reason behavior cloning is not smooth is because the function class that we consider here to learn the policy is highly expressive. Typically, we use some black box method like neural net or decision trees, and in trying to maximize the accuracy, it actually reacts to all the small changes in the state feature. Okay, so in our paper, we propose a way to achieve smoothness by essentially functional regularizing function classes. Essentially regularize a complex policy class F, such as neural net, with a smooth and simple model class G, like a linear model. And similar to standard regularization, we can think of this new policy class, pi, as trying to output an action that is close to both f and g, where closeness is controlled by a regularizing parameters lambda, similar to standard regularization. And then we learn this regularized policy in an iterative loop in a fashion actually similar to Dagger or CERN that we discussed before. One big difference is that we develop a way to actually use simulated expert feedback so that we don't need interactive expert guiding the algorithm. And in each loop, we execute the current policy, and then using these trace and the expert feedback, we re-estimate the parameters of the regularizer G, and then we update the parameters of the complex function f. We then combine f and g to form an updated policy we call it pi hat, which will then be interpolated with the old policy to form a new policy in a fashion similar to Dagger, to CERN. And so in our paper, we proved that the algorithms actually achieve monotonic policy improvement, and the learning rates can be set adaptably for faster conversions compared to standard imitation learning algorithms. After a few iterations, the algorithm is able to quickly learn something that strikes a balance between accuracy and smoothness. Along the theme of regularizing function classes, there is also a recent work presenting at this conference by Verma et al., where the authors propose a method to imitate a black box policy trained by reinforcement learning, and regularize the imitation by a symbolic program. The result is an interpretable policy on top of a good imitation performance. For example, one can be viewed as a series of if-then-else statements which can be used to verify and guarantee correctness of the policy. And quickly, what if we want to have safe training and good imitations together? This is one goal of a paper titled Query Efficient Imitation Learning for End-to-End Autonomous Driving by Zhang and Zhou in 2017. The task is to imitate an expert in the torque driving simulation environment to learn a driving policy which maps the images from the front camera to the steering angle. And similar to Dagger, we have an expert policy pi star that's guiding the process. The key issue here is that there are instances during training that executing the learning policy will result in unsafe behavior. For example, the car may veer off the road or crashing into a nearby vehicle. So the idea to fix this is to train a separate classifier, CSIF, which outputs at each frame how likely the current policy is going to deviate from the expert by some threshold amount epsilon. And CSIF is trained by collecting sample from CSIF star, which simply indicates whether the current policy pi and pi star would differ by epsilon, which we can do during training. And then we can use binary cross entropy loss as the objective to train CSIF. And then the way to incorporate safety into training is then pretty straightforward. The principle is in current state, if CSIF returns 1, then we drive using our current policy pi. Otherwise, the expert policy pi star will take over, and the current policy is considered unsafe. And so basically, the authors propose an algorithm called Safe Dagger based on this principle. And the key difference between Safe Dagger and the original Dagger is that we use a safety classifier to decide whether states are unsafe, and then we only query experts at those unsafe states. So we can think of this as an active version of Dagger. The result is that Safe Dagger is able to learn a policy using less number of queries compared to the original Dagger. And also the number of damages during training is also much lower compared to behavior cloning and Dagger, compared to both behavior cloning and Dagger. Okay, so next we're going to talk about multitask, transfer and meta imitation learning. First, consider this block stacking task where we want to stack 6 blocks into 3 towers with this particular color ordering. But the initial condition and location of 3 towers may differ from one trial to the next. So we consider this to be the same task, and these are 3 different instances of the same task. And now, what happens if we also want to handle similar tasks, but we want to stack 1 tower of height 6 instead of 3 towers of height 2, or 1 tower of 4 and then the other one of 2, etc. So the traditional learning approach is to collect many demonstrations from each task and then train a policy for each one of them separately. And in the case where we have multiple related tasks, however, the question is, can we come up with a way to do this more efficiently? And the idea of one-shot imitation learning by Duan and all in 2017 is to pull together a distribution of tasks and then train a neural network policy so that at test time, the neural network policy can generalize from a single demonstration of a previously unseen task. So the way that training takes place is we assume during training we have multiple pairs of demonstrations from expert of 2 different instances of the same task. And the idea is we are going to treat this, the second demonstrations, showing here on the right, essentially as a validation trajectory. And the neural network being trained will take as input the first trajectory, which is from a different instance, and the current state of the second trajectory. And the neural net will try to output the corresponding expert actions of the second trajectory, which we do know during training. And at test time, the desired execution is very similar, except that now we only have 1 demonstration of the new task. And facing a different instance of the same task, we simply roll out the policy that we learned. A related work by Tobin et al. In 2017 takes this 1 step further and attempts to handle the situations when training can be done purely in simulation through virtual reality, and testing is done in the real world. So to handle this sim to real transfer, they train using domain randomizations with different lighting conditions and different surface texture, etc. And the result is something like this, where the network will map visual images to actions end to end. And also the human can give demonstrations only simply in virtual reality, like in the upper left-hand corner, instead of previously having to grab the robotic arms to literally demonstrate the task. Perhaps the algorithmic framework can be made clearer by viewing one-shot imitation learning through the meta-learning lens. And the key idea from 2 papers by Finn et al. In 2017 is to view multiple policy for related tasks as sharing a common initializations parameters theta, which is the policy parameters that we are going to find. And the goal is to find theta so that when we find a new task I, given a limited number of demonstrations for task I, a task-specific policy now parameterized by theta I can be quickly obtained from theta by a few, or ideally 1 gradient step on a task-specific loss, Li. And during training, we, similar to before, we're going to take a pair of demonstration of the same task and alternatingly use gradient descent to first simulate the fast adaptations update rule from theta to theta I using the second rules here, and then use that new theta I. In turn, we're going to turn around, use a theta I to go back and perform gradient descent on the meta objective. There's also a recent extension of this meta-learning approach to the setting where instead of having human teleoperating the robots to give demonstrations, The authors proposed to do one-shot imitation learning in the transfer context, where the human give demonstration in natural state, and the robot has to learn the task via mapping the video of human performing the task to the right joint action. So this is a group of papers that handle one-shot imitation learning in various different settings. And before moving on, I want to touch on a paper from NIPS 2017 from Amin et al. In the inverse reinforcement learning setting. And so in this case, say we have an unknown reward function theta star, and we talked about before in the first half of the tutorial, uncovering theta star from single task inverse reinforcement learning is not a well-posed problem, right? But the setting addressed in this paper is a little bit different in that what if we have multiple tasks corresponding to multiple environments which may have different dynamics? As the motivation is, this common parameters, theta star may represent something about the latent human preference in terms of how humans want to communicate to the robot. So then the goal for us is to learn theta star from demonstration from as few tasks as possible and generalize to a new one. And the authors consider two different settings where the agent can choose to learn the task actively, which is the easiest setting, or the more difficult setting is the nature can reveal the task adversarially. So this is the problem that the paper discussed. So next, I'm just going to discuss another imitation learning settings where we may have multiple agents interacting in the environment, or the behavior may exhibit multiple different modalities that doesn't quite fit into the traditional imitation learning setting. Let's first consider imitation learning problem here where we have multiple agents coordinating to achieve a common goal. Let me see if the video would play. Oh, it does. An example is a predator-prey game with 4 predators trying to corner a common prey. And perhaps a more interesting example here we're going to focus on is learning multiple policies from tracking data of real-life professional football. So the data here is from the Premier League in England. We have the red team attacking from left to right. The blue dots are the actual defending team. And the white dots are the test time policy learned using the method proposed in our paper called Coordinated Multi-Agent Imitation Learning from ICML 2017. So the biggest problem when we want to adapt imitation learning to coordinated setting is that the expert demonstration often contain raw information that is implicit and we don't get to observe. For example, the notions, take the example of football, the notion of defensive midfielder, in a way, if you think about it, is a poorly defined notion, right? And also, coordinating agent may switch or swap role during the same trajectory. So if we want to lift imitation learning from single agent to multi-agent setting, one of the properties that we usually take for granted during using black box methods is somehow the neural net or decision tree will be able to take a state representation that already has a right ordering, right? And this is fine if we fit into a say a vector of words, embedding or etc. But in the multi-agent context, the issue is that we don't really have a natural way to have semantically consistent input representation. For example, the feature vector of agent acting in row 1, for example, should come into the first slot, and the second row should correspond to the second slot, etc. And this is the kind of ideal scenario that we want. However, in reality, if we don't have this raw information, what we actually have, what we're facing, is all sort of permutation of the demonstration data that may make the learning process very, very noisy. So we don't really have access to the latent raw information. And what can we do in this case? And the idea, the proposed method that in this paper is to combine imitation learning with unsupervised graphical model of inference and learning. The graphical model encodes the latent raw information where we optimize the policy and learn the graphical model in an alternating fashion. So in particular, for each iterations, if we fix the graphical model parameters, then we can solve a small combinatorial optimization problems to assign the right index to each agent. And then we can use any imitation learning algorithms conditioned on this indexings to update the policy for each agent. We then execute this policy, and we use stochastic variational inference to jointly fine-tune the graphical model's parameters again. And each optimization step is done in a loop, and it can be done in a mini batch to speed up training. And just so you can visualize in the football applications, this is what the latent information would encode. So basically, we learn in an unsupervised manner that the average formation from the British Premier League is roughly correspond to the 4-4-2 formation. Okay, so here I just want to show an example of what happened if we ignore this implicit coordination during training. You can see on the left-hand side that the joint actions become severely uncoordinated, and basically the imitation learning problem essentially collapses. A quick mention of a recent work by Zhang et al. Dealing with multi-agent imitation learning setting, but now they're trying to learn a generative model instead of just learning to mimic agents, to mimic the experts, and to learn a model for generative imitation learning. So typically, the agent has to infer high-level intent that dictate low-level actions, right? And this high-level information is also frequently a latent variable. So I want to illustrate this point via an extension of generative adversarial imitation learning. I don't know if you could see the video very clearly, but here we have the torque driving simulation again, and the driving demonstration in this case will consist of two different modes, either passing on the left or passing on the right. And we can view this decision of passing on left versus right as a latent variable, z, that once conditioned on this variable being 0 or 1, the resulting behavior of the same policy will kind of branch out differently. So one reason that original Gale approach doesn't work too well in this type of problem is that vanilla generative adversarial networks tend to have trouble telling apart different modality from the data. And so instead, the suggested method here is to augment the original Gale objective with additional regularization by trying to essentially maximize the mutual information between the latent variable z on one hand and the state action pair that is generated by the policy on the other hand. And this mutual information quantity, even though is intractable, it can be approximated by some variational lower bound. And so the GAN training objective is additionally replaced by Wasserstein-GAN to remedy the mode collapsing problem that I referred a minute ago. Another improvement from original Gale is that the policy now can take high-dimensional visual input data. So to summarize the result, you can see here that the policy being learned was able to differentiate distinctly between the two modes of passing on the left versus passing on the right. And one side benefit of learning the latent variable, to go back to the subject of generative imitation learning, is that now we can use this to generate different type of behavior which is not seen during training. In particular, if we use z equal to 0.5, the ensuing behavior will be something that interpolates between z equal to 0 and z equal to 1. So I move on to some other topics, but if interested, you can also see other recent paper related to this theme here. Now, I'll discuss some recent work on the subject of inverse reinforcement teaching, in quotes, and the reason is that this is not really a term. This is something that I made up to capture the theme of the subsequent papers, that trying to figure out the right way for human to teach machine. or to communicate the reward function to the machine, which is related to the inverse reinforcement learning problem that we talked about in the first half. Okay, so we already talked about how learning a reward function from human demonstration is a useful way to learn behavior instead of manually specifying the reward function, right? Now, the question of interest here is, how should human demonstrate the task? And usually in inverse reinforcement learning, as we touched on before, the assumption is the expert demonstration should correspond to an optimal policy or a near optimal policy. And the robot, as a passive observer, would learn the implied reward function from this human's optimal trajectories. However, one subtle problem that may arise is that by efficiently demonstrating the task, human actually may ignore useful teaching behavior. So, for instance, think of this example of the cooking robot. Instead of just showing the optimal path, how to make pasta, human may be better off explaining the steps in cooking, or showing the robot what to do when we run out of ingredients, for example, etc. So the question here is, which path should the human take to actually teach the reward function to the robot? And from this starting point, the authors of this paper, Cooperative Inverse Reinforcement Learning, formulate the problem as a two players game where the human and robot may take turn demonstrating the task and estimating the reward function. And it's an asymmetric game in the sense that the human has access to the true human reward function, but the robot only knows a prior distributions over the human rewards. And actually, this is the key to make the learning problem is tractable than a general Markov game. And under the assumption, in this particular paper, under the assumption of linear reward function, the authors show that when demonstrating the behavior to the robot, humans actually should take into account the robot's posterior inference of the reward into showing the demonstrations. And under certain settings, the interesting conclusion is that this amounts to a different optimization objective than simply maximizing the human rewards. I just quickly note here that an extension of this work is also presented this year here as ICML. A related paper from Hoang et al. In NIP 16 also take a Bayesian perspective to learning and teaching and arrive at a similar message, which is that an expert who is motivated to teach will or should take into account the learner's inference about what's optimal, which is called demonstrations or doing here. And so in this work, one interesting aspect of extra aspect of this work compared to the previous one is that the authors conduct experiment using humans to confirm this hypothesis, where depending on whether the instruction is to do the task or to show someone how to do the task, will result in different setup behavior, as you can see in two different setup trajectories here. Okay, so up until this point, the feedback that we assume from the expert usually takes the form of optimal or near optimal actions. And as we try to teach machines to do useful things, there are other type of feedback that makes sense for human expert. And we're gonna, in this last topic, we're gonna focus on a few alternatives of expert feedback. So starting with a paper that we are going to present in this conference in a few days, the central question that we study here is that how can we most efficiently make use of expert feedback? And the starting observation is that very often humans give feedback with a natural hierarchical structure assumed. For instance, if someone asks you how to navigate to the restroom, most likely you'll give instruction based on certain signposts, like going to the end of the hall, make a left until the corridor and make another left, etc. And this is pretty much in contrast with a typical flat reinforcement learning or imitation learning setting, where planning is supposed to happen step by step. So to illustrate this point further, consider this navigation scenario where the agent represented by a white dot in the bottom left corner has to find its way to the yellow block. and say the agent is making its way and stumble around and then get stuck in one of the room, then flat imitation learning algorithm will require that the expert provide corrections for individual mistakes along the way, and so the effort required from the expert would essentially be proportional to the task horizon, right? And the question here is, can we do better than this? And given a hierarchical structure, we indeed can do better. In this case, we would want to have a high-level policy that decide which macro actions that we're going to take. For example, a macro actions in this case would correspond to go to one of the exit door given the room that you're in. And in this paper, we propose a type of expert feedback that essentially requires much less effort from the teacher. For instance, after the agents pick some macro actions, the low-level policy would execute the low-level actions, and when upon completions, we only ask a teacher to verify whether the macro action has been completed successfully or not. Basically, an up vote or a down vote. So the idea is to ask for feedback that is much weaker than providing the full low-level details. And the key insight here is that verifying in this manner is actually much cheaper than labeling the micro actions. And the second key insight of our algorithm is that the experts should mostly provide high-level feedback and only zoom into low-level when necessary. And intuitively, when the agent has picked a good subtask, but not being able to complete it, that's the only instance where the expert or the expert should really micromanage in this case. And we show that these ideas allow significant saving in terms of teachers' effort as measured by the amount of feedback provided. And we also extend our approach to hierarchically composed imitation learning at the top level and reinforcement learning at the low level, and apply it to the challenging Atari game Montezuma's Revenge. And we show that using only a modest amount of expert feedback, the algorithm can still learn significantly faster than using pure reinforcement learning. Another example of learning from weak feedback is the work on learning from human preferences from Cristiano et al. In NIPS 17. And again, here we want to teach useful behavior to the learning agent without requiring so much effort from the human teachers. The method here in particular infers a reward function from human evaluative judgment by showing the human evaluator two different set of trajectories and asking the human to provide pairwise comparison instead of numeric feedback. And in many cases, this preference feedback, as you can imagine, is much easier to specify than strictly numeric reward that we see either in standard reinforcement learning setting. The unknown reward, so the particular method that the authors propose in this case, the unknown reward function R is viewed as a latent factor explaining human judgment. And the hypothesis coming from Bradley Terry's model is that humans' probability of preferring a trajectory tau 1 over tau 2 depend exponentially on the value of latent rewards, summing over the length of the trajectories. And from here, we can estimate the reward function, the latent reward function, by minimizing the cross entropy between these predictions and the actual human judgment collected from the data. And the takeaway of the result is that using this technique, we are able to learn a good reward function using not so many human label. You can also check out some previous work using this type of preference feedback from previous conferences. And last, on the subject of natural feedback, I'd like to talk about Coach, an algorithm from a paper called Interactive Learning from Policy-Dependent Human Feedback by Mark Glassens et al. From last year's ICML. The motivation here is to teach robots to do tasks, taking inspiration from animal training. And to start with, the author ran an experiment with human subjects And here's an example of the interface on Amazon Mechanical Turk, where the dog is supposed to go to the goal in yellow without crossing the lawn. And humans can give discrete rewards or punishment. And turns out the empirical result is that human feedback tends to be policy dependent. In particular, what that means is that human feedback may be differential, meaning that positive feedback is more frequent when the dog is improving from bad dog to good dog instead of from okay to good. Or human feedback can also exhibit diminishing return property, meaning that as the agent adopts good behavior, positive feedback may become less frequent. And this is quite different from what we saw from other imitation learning scheme previously discussed, where humans is supposed to give optimal feedback consistently, right? So from this empirical result, the author note that the advantage function in reinforcement learning is a good feedback model in that it fits these criteria. And in case you're not familiar with advantage functions, it simply is the difference between action value function Q and state value function V, which basically show how good taking an action A is compared to the expected value. And now the strategy of coach is to have humans supplying the rewards and to teach and to treat human feedback as an approximation to the advantage function. So from this starting observation, the idea is to start with the policy gradient theorem, which we saw from the first half of the tutorial. And now to update the policy parameters theta, we will use gradient descent as usual, except that the advantage function is replaced by some discretized human reward or punishment. And the assumption here is that those discretized human rewards, which obviously are much more natural for human to supply than numeric values, will be equal to the actual advantage function in expectation. So here's one experiment using coach. Just to describe to you the setting, the human is trying to train a robot, in this case the turtle bot, to hide away from the ping ball. And human is giving discrete feedback, which is either this red circle or the blue square using a Wii controller. So it's discretized, I believe it's a binary feedback. And so, for example, punishment is given when the robot moves toward the ball, and reward is given when the robot does correct behavior, for example, move away from the ball or turn away when the ball is sufficiently far, and etc. And here is a short clip of the result.
After this very short training period, the turtlebot has learned the correct responses to all the stimulus, and we can test it by putting the ball directly in front of it, which causes it to move away, turn when it's farther enough away, and then stop when the ball is out of its vision.
You can check out more complicated experiment in the paper. And I just want to point out that a paper that is a predecessor of Coach called Tamer, which uses related ideas using human feedback to directly learn a policy to overcome credit assignments of reinforcement, credit assignment problem of reinforcement learning, if you're interested. With that, I would like to summarize. And so far, hopefully, you have seen from this tutorial that imitation learning is a broad research area with many interesting research questions. And although we didn't really have time to compare directly against reinforcement learning, it's been our experience that imitation learning is a much more practical approach compared to reinforcement learning, to pure reinforcement learning, when it comes to certain criteria such as sample complexity, cost of doing experiment, or the requirement of having a simulator, etc. And as you have seen from Yisong's description and myself, imitation learning has found a diverse range of applications well beyond video games or other simulated environment. And with that, I'm going to end here, and we are happy to answer any remaining questions that you may have.
Sorry for going a little over time. If you need to leave, of course, please feel free. But if you have questions, we're happy to stick around for a little while to answer them.
exactly 1 hour. I was through up because we paused this, so I had no idea.